Okay, now let's have a look at something a little more tricky. So we're going to look at the superposition of two vibrations which have different frequency. So you'll notice that just for fun, we've changed how we're describing our functions to use the cosine version. And that's just because a little bit later it's going to be easier for us to be using cosines than sines. And this is partly because of this rule, which says if you've got cosine of a plus b, that's equal to cosine of a, cosine of b, minus sine of a, sine of b. And we'll see how we can use that in a little bit. So what can we say about this situation? Well, we can't add them as simply as we could for the case where the angular frequencies are the same. So as far as amplitude goes, we can just say, well, obviously the amplitude of the resulting wave must lie between the sum, so the kind of maximum possible amplitude which we'd have, which would be a1 plus a2, and the smallest possible amplitude that we could have, which would be a1 minus a2. And other than that, we can't really say an awful lot. Let's head over and have a look at what happens on our Geogebra applet when we have different frequencies. Okay, so let's keep our amplitudes the same for the moment, and we can keep our phase shifts the same. And now let's see what happens when we start changing the angular frequency of one of our functions. Well, you'll see straight away that we're no longer getting a plain sinusoid. We're getting what definitely looks like the addition of different sinusoids. And our resulting function doesn't have a period that is the same as either of the other two. If we do some phase shifting, you'll notice that the phase plays a big role again. So we might have quite different functions depending on how our phase shifts. And we haven't even started playing around with our amplitudes here, but our amplitudes can also have quite a big effect. So you can see why it's a little more complicated to talk about functions which have different frequencies, but we can say a few things. So the first is what we've just really said, which is if we have a very simple relationship between our angular frequencies, maybe like one is twice the other or something like that, then we can usually calculate what's going on, but otherwise our displacement is just going to be some complicated function of time. As we've seen, there's a strong dependence on phase, and just changing the phase a little bit, even keeping the angular frequencies where they are, can seriously change the resulting wave, as we saw in the example. Now, if it turns out that there is some periodicity, so there is some integer number of times the period of the first wave, which is equal to some other integer number of times the period of the second wave, then the resulting complicated wave will have a period t. This is not saying that it's going to be sinusoidal, as we've seen, but it will have a repeating period where it might do a kind of funny jiggle thing and then do the funny jiggle thing again, and so on and so on. But this is not guaranteed, because it might be that the time it takes for both of the component waves to kind of go through the same number t of full periods is just too long. So it might not have a periodicity that we can see. There is one particular case that we can look at that's quite interesting. So if we've got our two simple harmonic motions and they're close in amplitude and close in frequency, then we observe what are called beats. So again, we're going to consider this using two simple harmonic motions, and we're going to give them the same amplitude, but slightly different frequencies. So we're really thinking of omega 1 and omega 2 as being very close. So before we go and do the maths, let's see what our Geogebra applet says if we do this. Okay, so I'm going to put my amplitudes back to be about the same, set them both equal to 1, and we're going to assume that they have the same phase. And let's get our two amplitudes quite close together. So I'm going to make them quite big so that we can see. So I've got omega 1 is 3.7, and let's make omega 2 about 3.6 if we can, or 3.5 will help us see. And now what you'll notice is that we've definitely suddenly got what appears to be a sine wave, but modulated in amplitude in a way that also seems sinusoidal. So if I was to keep moving so that you can see the rest of this graph, you'll notice the amplitude goes way down, and then it starts growing again, and then it goes way down again. So what we can see from this is that if our angular frequencies are very close together and our amplitudes are close together, we get a resulting sinusoid for our sum that is modulated in amplitude in a sinusoidal way. So let's see if we can figure out the mathematics behind that. So if we add our two simple harmonic motions, so remember we're using the cosine form here, then we're going to get x1 plus x2 is equal to a cos omega 1 t plus a, oops, not sine, cos of omega 2t. And if you play around with some of your double angle formulae and things like that, and you do a bit of work, what you'll find is that this is equal to 2a cosine omega 1 minus omega 2 over 2t times the cosine of omega 1 plus omega 2 over 2t. So I'm not saying that this is quick, but you could also just check that if you multiply this out using your adding of angles formula, then you get the top thing. So let's have a look at this, because this is actually quite interesting. So notice we've got our twice our amplitude, and then we've got a cosine over here which has an omega 1 minus an omega 2, and over here we have another cosine with an omega 1 plus omega 2 over 2. So what does this end up? Does it give us the thing that we just saw in the Geogebra app? Well, firstly, notice that we haven't said anything up until now about making omega 1 and omega 2 very close. So the previous slide, it holds for any values of omega 1 and omega 2. But we're only going to get beats if we have that the distance between omega 1 and omega 2 is much less than the sum of the two. So we want to have very small distance between, so our two angular frequencies are very close together. And when this happens, what we find is, so here's an example. We've got our two constituent waves here, and you'll see, I mean, they've got the same sort of amplitude and very close frequencies, and we end up over here with a wave that has a similar frequency, it seems, to the two original ones, but it's also modulated by a much longer period oscillation. And in fact, you can figure out that this first term that we have over here is in fact what is modulating our amplitude. So this omega 1 minus omega 2 is going to be very small. So if you think about it, that means that there are very few, it takes a very long time for one complete oscillation to happen. Whereas omega 1 plus omega 2 is going to be quite big, so that's going to be faster. So our combined displacement fits into an envelope defined as we see here. So this is really kind of a modulated amplitude of our resulting wave. Things to notice: what's called the beat frequency is the difference of the individual frequencies. So the beat frequency is that modulated thing that you hear. So if, for example, you have two tuning forks, one at 255 Hertz and one at 257, then the beat frequency is 256. And it passes through maximum loudness twice per second. So here's something for you to try. We've got two vibrations along the length of fishing wire described by the equations. Y1 is a cos 14 pi t, Y2 is a cos 16 pi t, and you can find the period of the beat and sketch the displacement during this period. So pause the video and see if you can figure that one out. So you can check your answers over here. The beat frequency is 1 Hertz. So our beat period is 1 second. So you're going to hear a kind of a loud thing every 1 second. And if you sketch, you'll see that. So beats actually have quite a lot of use, particularly in music. And there's a YouTube video for you to watch so that you can actually hear beats when you've got two tuning forks that are close in frequency, and you'll actually hear this loud, soft, slower vibration going on. So go and have a watch of that YouTube video and then come back here for the last little bit.